So in this tutorial, we will work with the command line. So let's have SHELIXIR and SHELIXCDE properly installed. And in the beginning, just run command SHELIXIR to see the help. So there is a number of parameters you have to feed the SHELIXIR. So if you want to run something, you first set prefix, name of your project, and let's keep it PSE14. So this is the shortcut for my protein. I don't want to set the output directory path, but I have a set data set PSE14 HKL. So I don't need all the other files, but the number of processors, this is something what I would like to limit, because my computer has 3 CPUs, but I want to use just 3 of them to keep some computational power for any other purposes. The other thing you must set up is the nature of your heavy element. This you can do with the SAC keyword, and in my case it was selenium. Then you have to set up the number of atoms to be searched, so fine. And it's this is a urea soak, but in general it's always recommended to try to find a bit more atoms than expected. In my case, I don't know, let's put 50 in there. Then the number of trials for searching of the substructure. In my case, I don't know, let's hope that 200 will be sufficient. If not, you should increase this number. In case your input file doesn't contain the information about the unit cell parameters, you can supply these unit cell parameters with the keyword cell, with the parameter cell, and then 40, 50, whatever, it's up to you. In my case, I already know that almost all files coming from the XDS are in a form that SHELIXIR is able to read out the unit cell parameter. Sometimes you need to set the wavelength, and there's a number of other parameters you can set up. But what is actually crucial is to set up the SHELIXIR parameters. In this case, don't forget to use the quotes here. Let's skip this for a while, because we will come back to this thing a bit later. What we also need to set is to select the space group we want to screen, and in this case you may select the Pravert type, and here we have shortcuts like usually in the XDS, so it might be cubic primitive, whatever you want, you believe it is. In my case, it's orthorhombic primitive. But let's say I want to try only some of the space group and not all the possibilities. So you can, in this case, you may use a parameter argument list and put everything to quotes, like P1, C2, I don't know, P3, whatever what is allowed by your unit cell parameters. So this is another possibility. So I do P2 to 2 and P to 1 to 1 to 1. just for example. As I see, let's come back to the parameters of the SHELIXIR routine, so EPAR, and here you need to use the quotes again, because otherwise the program will not read it as uh, all together. And here I prepared the list of most frequent SHELIXIR parameters, and in my case, let's keep all the calculations short. So let's do only 2 cycles of routine with 5 iterations of the density modifications. And I know that the heavy atoms are present in the native structure, and yeah, let's keep it short this way. Usually it's recommended to set some solvent content, but the great advantage of SHELIXIR is that you can screen for the optimal solvent content. In this case, you can do it with the following command. Either you use a command solve photo, and this will screen from 20% to 80% with a 5% step width, but I want to keep it simple, so let's do solid screening with the starting solvent content being 40%, the maximal solvent content 60%, and with the 10% steps that will also always use 3 CPUs of my computer, and we should be ready to run the analysis. I have here SHELIXIR running, and here you can see in which phase you are. Right now we are checking the space group P222, and it's running the SHELIXIR routine. Based on the information in the data, the current resolution was 2.10 angstrom, and right now we have SHELIXD routine, which was not successful apparently, and here we know that currently SHELIXE routine is run. Every run produces a directory with the name results underscore and the name of your job. In this directory, all the necessary files are available. So let's go to this directory and have a look what is in there. The calculations are still not finished, but you can go through the log files that are present there. Let's almost immediately after the running of this command, there is also an HTML file that sums up all calculations that are already finished. So let's check them. We see that the job is still running here. Here are the main arguments, or let's say parameters of our calculation. And here in this case, you can see the list of the space group which will be screened. We start with the space group P222, but we also have P2121. In this case, space group, nothing was calculated yet, but let's check the results from the space group P222. For every single run, you have here the input file for the SHELIX CDE procedures available. Here is the input file, and here is the log file. All the graphs are based on the logs file log files provided by the SHELIX programs, and you can check whether the graphs are also plotted correctly or not. So there's quite high anomalous signal if this space group were correct. The same situation here for the SHELIXD routine. We have here the input file available, and in case something went wrong and you wanted to change something, the input files are already prepared and you can check them, modify them, and run all the calculations again. Here is the log file for the D routine. So you can go through it and check. And the graphs that are usually shown also in other tools like HKL2Map, etc. This site is regularly updated until all the calculations are finished. But now we will have to wait until everything is done. Right now we can see that also the SHELIXE routine in the space group P222 is already finished, and we can see that there is not a big difference between the original and the inverted solution in various solvent contents. And here also the number of atoms built as the solvent content is not significantly different between the original and the inverted solution. So let's hope that we will be able to find correct phases and the right structure in the space group P212121. Here, of course, the strength of the animal signal is not different between these space group, at least from what's provided in the SHELIX C log file here again. But here, when looking at the SHELIX-D procedure output, we can see that there is a very high probability that our structure was, at least the heavy atoms, were found successfully. Let's check the SHELIX-D log file here. And let's go down. And we can do from these numbers and other numbers here that the solution was probably found. We also have a plot of site occupancy versus site number here, and once you see a significant drop, then it usually indicates the correct heavy atom determination. In this case, when it was urea soak, you may expect that the drop between different sites, site number, will not be that significant as in all the other cases. Unfortunately, the SHELIX-E routine is still not finished, but we will have to wait for it, but everything looks to be promising. And finally, we see that the SHELIX-E routine is finished here, and from the plots here, like contrast versus solvent content, we see that the structure was probably phased. What I especially like on SHELIX-E is that it also provides you the number of atoms built, because quite frequently the difference here in the number of atoms built is much more significant than when comparing the contrast between the original and inverted solution. But let's keep in mind that we will be looking for the original solution, original hand at the solvent of 40% here, and let's have a look on the files. And we also see here that all the calculations are finished. So this is the files we have here, and so now I'm in the right directory. Let's have a list of the files, as this is in two different space group, and multiple solvent content was analyzed. It offers much more files than usually, but we have to keep in mind that we were looking for solvent content 40%, and in the space group P212121. So let's use COOT to display the structure. And the result seems to be somehow promising. Okay, we also have the heavy atoms there. Let's try to load the maps. We have to keep in mind that it's 40 in the space group P2121, so it should be this file. And have a look on the structure. Although there are some regions where it doesn't look really great, there are also some regions in which you can start to build your side chains. And what else you can do to prove your solution being correct is to display the solvent in large distance from the molecule. So let's click on parameter and display something like 60 angstrom away from your molecule. And here we can see that there are big regions in which we don't see the electron density at high levels. So most probably the solution was really found. So that's all. Thank you for attention, and I hope you will be using SHELIXIR to make your life with Shelix a bit easier, but also to find the optimal phases. And if you wanted to know more, feel free to write me an email, and I will be especially happy for any criticism, because so far nobody has ever responded to anything. Bye.